Yeah, dear students, welcome to the second hour of day one class. So in the first hour, we learned that finite element method, right? Finite element method is a bit brief details of finite element method. So what is the finite means? So a finite number of elements are considered. Okay, we solve a problem at specified number of points. Okay, we are converting from an infinite number of points. Actually, in a space we have an infinite number of points, right? We are dividing that one from, we are converting from infinite number to finite number. We are considering just finite number. That's why we call finite number of finite element. So what is element? So we divide this one into number of simple like this one, simple elements. Okay, so it can consider that one is known as meshing, okay, or discretization. Okay, so we divide this one into a simple element. So we use an element to divide a space into number of specified points. Okay, so simulations are performed at a limited number of nodes, okay, instead of infinite number of nodes. So its method, what is method? Method is a numerical method. So as I said, numerical method only gives approximate solution. Okay, so that is the concept of finite element method. We divide a space into finite number of elements. Okay, and we use a numerical method to solve displacement, okay, or temperature or fluid velocity or anything, okay, to solve displacement at each node of a element, okay, at each node of the division. Okay, so like this one. So we are dividing this one into number of elements. Okay, so number of elements are different, number of nodes are different. Okay, so you may know, right, what is the difference between node and element. I will explain. So this is a node. Okay, this is a node, this is a node, but this one is only one element. It consists of 3 nodes. Okay, so what is the element? So as I said, right, element means we divide the space into number of elements. Okay, so based on the problem, we can consider a line element or a triangular element for 2-dimensional problem, and a brick element like this one, or tetrahedral element like this one. Okay, prism, triangular prism, or brick element. So to simply understand, so if you have a rectangular body, 3D body, we can consider a brick element. Okay, so that is we divide this body. So this one is a very complicated shape. So instead of considering a straight lines, we consider like this shape. Okay, curved shape. So there is a difference between straight shape and curved shape. Okay, suppose this one is a rectangular element, right? Rectangle. But when we consider curved shape bodies, so that can be changed. The shape can be changed like this. Nodes are fixed, right? For rectangle, 4 nodes, and this one also 4 nodes. But this one is different. Okay, this one is different. It's not straight shape. So that's why we call this one as a quadrilateral, not rectangular element. Okay, quadrilateral. So quadrilateral means the line is not straight. Okay, different line. And so based on the type of body, so we divide that body into number of elements. Okay, so simple elements. So an element is basic building block of a finite element analysis. Okay, here when we consider this one, right, a simple this one. So when we zoom it, it can be like this one. That is the element. Okay, so or mesh. So node. So here, yeah, we have a element here, and there is a connection point. Okay, so when we have another element, so there is a connection point between 2 elements, that is called a node. Okay, the adjacent elements are connected at each other by using nodes. Okay, so simply a node is a coordinate location, right? So coordinate So here we have xy, right? Xy. So if you want to know the position of this node, we specify this one to x1, y1, okay, coordinate location. Similarly here, x2 and y2. So we solve for the displacement at each node, okay? We do not solve for entire element. So, I mean, we do not solve the displacement here or here or here. So only at nodes we solve for the displacement, okay? Here only we solve. And if you want to know the displacement inside, we just interpolate, okay? So using shape functions, we call the shape functions. So we just interpolate this displacement. I want to find, okay, displace in the middle. We do not solve explicitly, but we use an interpolation method to solve for the displacement, okay? So it's a coordinate location, and at each node, we can connect another element, okay? Here, so at a particular node, we specify a degrees of freedom, okay? Degrees of freedom. So what are the degrees of freedom? I will explain what is the meaning of degrees of freedom. We specify the degrees of freedom at here and here and here. We solve for the degrees of freedom, okay? And the field variables, okay? So we say field variables. Field variables means, so in case of structural analysis, displacements, okay? You want like displacement. You want V1 means y direction displacement, u1 means x direction displacement, y direction v1 means y direction displacement. So these are the field variables, okay? So in case of structural analysis, displacements are field variables. In case of thermal analysis, temperature is the field variable. Temperature at each node is field variable. In case of fluid, fluid dynamics, in case of fluid dynamics, we find the velocity of fluid at each node, okay? In case of electromagnetic field, we find the electric potential at each node, okay? Electric potential at each node. So those are called field variables, okay? And boundary conditions, what is the boundary conditions, okay? So suppose here we have, I want to solve displacement inside this body, okay? This body. So actually this body is a part of, and so this one is actually the exhaust manifold, okay? Exhaust manifold. So exhaust pipe of a manifold means you can see many pipes, right? Exhaust pipe, exhaust, right? Exhaust pipe. So exhaust pipe of an engine. So all gases coming from the engine to the atmosphere through these exhaust pipes, okay? So this is exhaust manifold. So we connect this exhaust manifold to some engine, right? Engine. So we separate that one, and we are only solving the displacement on this exhaust manifold. So there must be some boundary condition because we are connecting using bolt and nut, right? So here we fix this one, okay? So that is the boundary condition. Similarly, based on the other body, okay, this body is connected to another body, right? So here, based on that body, we have some other boundary conditions, maybe fixed or something, okay, based on the other body condition. So those are the boundary conditions, okay? So we specify some values for the field variables, okay? So at the boundaries, so suppose here I want to specify here displacement is 0, right? Fixed means displacement is 0. So those are the boundary conditions for the field variables. The solution inside the geometry, okay? Here, the solution inside the geometry completely depending on the boundary conditions and type of material. So if the boundary conditions you specified wrong means the solution will get a wrong solution, okay, inside. Okay, suppose here instead of fixed support we use another boundary condition. If you use another boundary condition, you will get a wrong result, okay? So you should specify a correct boundary condition based on the situation, okay? Boundary condition changes based on the situation, okay? So that is the boundary condition. And you know, right, degrees of freedom. So what is the degrees of freedom? The minimum number of parameters are needed to define the position and state of an entity completely in space, okay? So is the definition is looking like hard, but here the degrees of freedom is nothing but a number of field variables I want to find at each node. Okay, so that's field variable number depending on the problem to problem. Okay, suppose when you consider a one-dimensional problem, okay, one-dimensional line, and I want to solve, and I apply force, and I apply force, and suppose I can consider a single node or two node or three node depending on the problem and depending on your choice. Okay, so by experience you will know. Suppose here how many nodes? So here one node and two and three and four and five. Okay, so this is a problem I'm going to solve. Okay, and what we have to find, and this is a one-dimensional problem and apply force like this one. We have to find the displacement in this direction. A load is applied only in this direction. Okay, load is applied only in this direction. I have to find u1. U1 means displacement here. U1 is 0, actually fixed, right? And U2, U3, and U4, and U4. Okay, so how many number of degrees of freedom it has? Okay, now we have 5 degrees of freedom. Okay, we have to find U2, U3, U4, U5. Okay, so if you consider a single element, okay, single element, it consists of 2 degrees of freedom. Okay, so it's Ui and Uj. Ui and Uj. Similarly, the force is not like straight, okay, not along this. Force is not always x direction, right? There may be like this one, x and y direction. Okay, x and y direction, like this one, random direction. So then what we have to find, because force is in random direction, we have to find the displacement at each node. We have to find ux and uy. Okay, ux, uy at one node. Actually, this is fixed, ux, uy 0, and ux, uy at two node, ux, uy at three node, third node, and ux, uy at fourth node, like that one. At each node we have then here also uxi and uyi. So generally ux means u and uy means v displacement, vertical displacement. U means horizontal displacement. So at each node we have to find 2 variables. Okay, so it consists of 2 degrees of freedom at each node. Okay, so it's depending on the problem to problem and also element to element. So similarly, if you consider a 3-dimensional, if you consider a 2-dimensional problem, and I divide this one into number of elements and consider a single element. Okay, like this one. So consider a single triangular element. Okay, because this is a 2-dimensional problem and I want to find, it consists of 1 node, 2, 3 nodes. So at each node we have to find u1 and v1, 2 displacement, u2, v2, and u3, v3. So total how many degrees of freedom? 6 degrees of freedom. Okay, that element has got 6 degrees of freedom. At each node, 2 degrees of freedom I had to find. Similarly, it is a 3-dimensional problem. Okay, if we use a brick element, okay, brick element. So brick element means, okay, I will show you. Brick element, okay, this one. So at each node we have to find, because it's a 3-dimensional problem, we have to find u, v, w. Okay, x direction displacement, y direction displacement, and z direction displacement. So total 8 nodes it has. So 8 into 3, so 21. 24. So total 24 degrees of freedom at each for a single element. Okay, for single element, and at each node 3 degrees of freedom, ux, uy, and uvw. Okay, so similarly, if number of elements are more, right, more degrees of freedom, because number of nodes are more, so it's depending on the number of nodes. Okay, not depending on number of elements, number of nodes. Okay, because number of elements are different and number of nodes are different, and number of nodes are connections, right? We have connection at each element. Okay, so like this one. So in this case, for example, let's consider a rectangular body, and I divide this rectangular body into like this one, 2 elements. Okay, so 1 and 2. So triangular element, let's say. So number of elements are only 2, but number of nodes 1, 2, 3, and 4. Okay, 4 nodes. So we carry it's a 2-dimensional problem. At each node we have to find ux and uy. So it consists of 4 nodes. So 4 into 2, 8 degrees of freedom. We have to find 8 variables. Okay, that is the 8 degrees of freedom. So it's depending on the problem to problem and number of elements, and element to element. Okay, so generally so it's number related to nodes, and also we consider structural problem, right? Structural problem means we have x direction displacement and y direction displacement and z direction displacement. Okay, but if we consider a temperature problem, so it's depending on the type of problem also, right? Here, so same element and same number of nodes we consider, and I am solving for structural analysis. We have to find at each node 2 degrees of freedom. Okay, for a 2-dimensional problem, at each node we have to find ux, uy, ux, uy at one node, ux, uy at the second node, ux, uy at the third node. But the same problem, same model, same geometry and same number of elements is used, same type of element is used, and same number of nodes, but the problem is thermal problem. So thermal problem is we just want to find the temperature at each node. Okay, 3 degrees of freedom it has. For a structural problem, we have to find, because displacement is a vector, right? ux, uy. So 2 variables at each node, but a temperature problem, just 1 variable at each node. So 3 degrees of freedom it has. Similarly, it is a fluid flow problem. We have to find velocity also vector, right? ux, uy. Okay, ux, uy. So 3 degrees freedom. So 2 degrees of freedom at each node, total 6 degrees of freedom. Okay, so yeah. So the number of degrees of freedom in FEM are based on type of problem and type of element, and yeah. So the displacement of node in 2D space is 2 values, or temperature at node is just 1 value. So generally, number of degrees of freedom for FEM discretization is number of nodes, okay, multiply number of degrees of freedom at each node. Okay, and this is also the number of degrees of freedom at each node depending on the problem to problem and element to element. Okay, and we have to solve for number of degrees of freedom. Okay, so next is what? Yeah. Okay, there is one more differentiation. Shape function. There is no slide related to shape function. So shape function is also important topic. Shape function means, suppose here when we use a triangular element, right? We're just only finding the displacement temperature at T1, T2, and T3. So only at nodes I am finding the temperature only at nodes, right? But here X and Y. This is the body, okay? A triangular body. Just I use just only one element. Okay. So I just only find temperature at each node T1, T2, T3. But actually we have to find the temperature of entire body, right? Anywhere in the space. Like I want to find the temperature here, but if you know the temperature here and here and here, we don't know the temperature here. So we use a safe function for that one, or interpolated function. We use interpolation, right? So like a temperature in a space, any point here or here or here. XY means any point, right? So is equal to N1 T1 plus N2 T2 plus N2 N3 T3. Okay, N3. So N1 and N2 and N3 are called shape functions. Okay, the shape functions are depends upon the shape number of nodes. Okay, number of nodes. Okay, if it is a 4-node element, we have to find 4 shape functions. Okay, N1, N2, N3, N4. Okay, so like that one. So if you know the N1 and N2 and N3, we can find the temperature at any location. Okay, not only at the nodes. So we define N1 and N2 and N3 in such a way that at a particular node, the N1 value, the shape function at that value is 1, and remaining shape functions values are zeros. Suppose here at this node, N1 is 1. So N1 is equal to 1. Therefore, when N1 is equal to 1, and N2 is equal to 0 and N3 is equal to 0 at this node, so only the temperature value is T1, right, at that particular node. Similarly here, N2 is equal to 1 and N1 and N2, N3 is 0. So therefore the temperature value is T2, and here N3 is equal to 1 and N1 and N2 0. So therefore temperature value should be T3. So that is the shape function. Okay. Yeah, these are the fundamentals of FEM. So we know what is the difference. Finite element method compared to other method is finite element method is suitable for complex bodies. Okay, when the body is having complex shape, we can apply finite element method, but applying the remaining methods for complex shapes is hard. Okay, so we need a special techniques for applying this type of. But finite element method, we don't need a special technique. We can apply a finite element method for complex shapes. That is the main method. And also nonlinear materials and anisotropic materials we can use. Nonlinear material means, you know, right? The stiffness is not constant. When we apply some load, the stiffness is different. When we apply another load, the stiffness. Similarly, the Young's modulus value, E value is not constant. Okay, so it's depending on the stress and strain developed. And anisotropic means, so the values, properties of material is not same throughout the body. Okay, so it's depending on space. Suppose Young's modulus values are different at different locations inside the body. Suppose here, when we consider here, the Young's modulus value is different. When we consider here, Young's modulus value is different. So then that type of material is known as anisotropic. So not only Young's modulus, thermal conductivity or some different material properties are there, right? All properties are not same throughout the body, then that material is called anisotropic. So generally all bodies are anisotropic. Okay, so there is the values are not constant throughout the body, but we assume all bodies are isotropic. Okay? Isotropic means all the properties are same throughout the body. So only special cases we consider anisotropic. Okay, so those are the advantages of finite element method. So as you know, finite element method, we write finite element method in the form of Ku is equal to F. Okay, so here this one is the known value. So based on the force. Okay, this F is known as load vector. Okay, load vector or action. So all type of finite element method, whether all applications, whether it is a heat transfer, fluid flow, or acoustic or electric magnetism, all types of material, all types of problems, the same form. Okay, we have to construct the same form, but based on the problem to problem, type of, based on the type of analysis. Okay, so these are different. So for structural analysis, U is displacement, but fluid flow, U is fluid velocity. For temperature, U is temperature value at each node, and for electrostatic problem, it's electric potential. Similarly, K is stiffness of material for structural problem. K is thermal conductivity matrix for thermal problem, viscosity matrix for fluid flow problem, and electrostatic permittivity. Okay, and F is force for structural problem. Heat source. Heat source means the amount of heat we are supplying, right, at a particular point. So that is a heat source. So Q for thermal problem, and some force, body force for fluid flow problem, and electric charge for electrostatic problem. Okay. And any finite element method, we divide a finite element method into number of elements. Okay, so in finite element method, any method, not only in finite element method, finite difference method, or all methods. So we divide a body into number of elements in order to solve. Okay, we are changing infinite number of degrees of freedom to finite number of degrees of freedom. We are considering a finite number of elements to divide the body. So infinite number means we cannot solve, right? So finite number of bodies, and based on the type of body. Okay, so we can consider type of element. Okay, so for line bodies we can consider this one, and based on type of load and all, we can consider. For two-dimensional bodies, we can consider a triangular element or quadrilateral element. Okay, for three-dimensional bodies, we can consider solid body. Okay, and also three-dimensional surface bodies, we can consider cell and plate elements. I will explain clearly what is the difference between three-dimensional surface and two-dimensional surface and three-dimensional surface. So we have surface means 2D surface, right? 2D surface means in a particular plane. The entire body is in a particular plane. We also have 3D surface. So the like round, when you consider a cylindrical body, it's a 3D surface, right? So the entire surface is not in a particular plane. So then it's a 3D surface. Then we have to use different type of element. Okay, so and what are the degrees of freedom? Number of degrees of freedom depends on the number of nodes and the type of problem we are considering. Okay, and if it is a one-dimensional problem, we just only solve for displacement. So if we consider a structural problem and one-dimensional line element, okay, line element, so we are only solving displacement in a particular direction. So at each node, we are only have 1 degree of freedom. Similarly, if it is a two-dimensional problem, okay, line element, so truss element like two-dimensional, at each node we are solving for displacement x and y directions, 2 degrees of freedom. Three-dimensional problem, 3 degrees of freedom, okay, at each node. That is the degrees of freedom. So the details of element types in finite element method. Okay, what are the details of elements? So as I said, right, depending on the problem, we can assume something, right? So we can convert a 3-dimensional problem into 1-dimensional problem or 2-dimensional problem, or just we solve 3-dimensional problem as it is. So depending on the type of analysis, okay, 1-dimensional or 2-dimensional. So we have different elements, okay. So first is line element, okay, line element. So what is a line element? Line element, suppose here, when we consider a car frame, right? Car frame like this one. So this one. So we can construct this body as a line instead of complete. Actually, this one has some cross section, right? So cylindrical cross section, circular cross section like this one. This is a 3D body. So this is a 3D body. Let's consider this one, a portion. Okay, 3D body. So, but what we are doing is when we consider line element or beam element, so that's depending on problem to problem. Okay, what is there is a difference between bar and truss, and line elements are 3 types. Okay, so I will explain what are those. So we can just consider a line. Okay, if the cross section is uniform throughout this body, okay, we can consider this one as a line, just line. Or you can also consider as a 3D body, but for the sake of advantage, okay, to reduce the number of degrees of freedom, we just consider that one as a line body. Okay, line body like this one. Oh, like the purple color. Okay, line body, and we just consider for a cross section for this one. If it is a circular cross section, rectangular cross section, like so this one. Okay, similarly here, okay, like this one. So when we use line elements, so line elements are used when the cross-sectional area, okay, right here, so length of the bar is very high compared to the cross-sectional area. Okay, slender bodies, we say slender bodies, right? Slender means the cross-sectional area is very, very small. I mean, the dimension normal to this axis is very, very small compared to the length of the bar. Okay, so that one. So we can just consider a line element. So in line element also, there are bar type line element. Okay, there are truss type line element and beam type line element. Okay, so what is the difference between these 3? So what is a bar element? Bar element or spring element? Okay, like this one. If a force is applied like this one, and force is along the axis, okay, so axially loaded bars, so then we can simply work in one-dimensional problem. This is a one-dimensional problem. Okay, so then this one is a bar element. Okay, so bar element at each node we can consider for solving u1. At 2 node we can consider for solving u2. So at each node only 1 degrees of freedom. Okay, because force is applied along this direction. So this direction may be different. Okay, suppose here the bar is in this direction, we are working on that direction. Okay, x is this direction. Similarly, if the bar is this direction, 2 bars, let's say. If the axis is like this one, and when we apply force along the axis, okay, so then we can consider this one as a one-dimensional problem. So just we consider a bar element. So to simplify the model, okay, what is a truss? There is a difference between bar and truss element. Okay, truss, you know, right? What is a truss? So like this. So let's consider this one. This one is one element, and this one is another element. Okay, so both are connected here. So we cannot simply work in this direction, or you cannot simply work in this direction, right? So because there is a connection point between these two, so we have to work in global coordinate system. Okay, so truss element is nothing but we convert the bar element into 2 dimensions. So here, so when we work, I mean, suppose here, this one is 1 bar, I mean, this one is another structure, and when we apply load like this one along this axis, so then we just simply need to work using bar element. Okay, but here the orientation is different between 2 structures, right? In this case, the orientation is completely different. So here along this direction, and here along this direction. So you cannot simply work either in this direction, or you cannot simply work either in this direction. So we have to change the orientation, okay, into global coordinate system. So we have a truss element. Okay, we have to use a truss element. So truss element is nothing but orient. Okay, orient this element in global coordinate system, and we have to find at each node u1. Suppose this one is first node, we have to find u1 v1 and u2 v2. Okay, at each node we have 2 degrees of freedom. If it is a 2-dimensional truss problem, it may be a 3-dimensional truss problem. Okay, so the line the line body does not remain in a single plane. Maybe it may be remain in a 3-dimensional plane. Then we have to find u1 v1 w1. Similarly u2 v2 w2. 3-dimensional problem, 3 degrees of freedom. So there is a difference between truss and beam element. Okay, beam. What is beam? So beam also is a line element. Okay, but the problem with the truss and beam is, so here suppose truss means we assume that load is applied along only here. Only load is applied at the joints. Okay, at the joints, and when all the loads are applied at the joint, we can work with the truss element. But here, let's consider this one. Here, this is joint here, this is joint, right? This is one joint, and this is another joint, and here another joint, and here. And load is not applied at the joints, and also load is not, I mean, the load is applied perpendicularly like this. So this is subjected to bending, right? Bending. So when we assume truss, we assume that the trusses are either in tension or compression. There is no bending because loads are applied at the joints, and all joints are pin time. Okay, pin time. So not fixed joints. Okay, pin time means just free rotation. Okay, but here the load is applied in the middle. So that means this joint, this bar is subjected to bending also. So when this bar is subjected to bending, so then what we have to do, we cannot simply consider truss element. We have to consider a beam element. Okay. So what is beam element then? So beam element, if we consider a beam element, so we have to find the rotation also. Okay. In a 3-dimensional space, we have to find theta, 2-dimensional phase, we have to find theta 1, and also rotation here theta 2, and also we have to find the deflection. So let's say we apply load like this. So x1 and y1, v1 and v2. So at each node we have to find 3 degrees of freedom. 2 degrees of, so displacement and as well as rotation of, okay, because this bar is subjected to bending. So bending means the bending direction is there, right? So we have to find the slope also. So at each node we have to find 2 variables. So that one is a beam element. Okay, beam element. So similarly, general kind of line element, right? So you know, right, bar and truss and beam. So but the general kind of beam element is known as frame element. Okay, this one is frame. So that means we have to find x1 and y1. So displacement at each node and w1 at each node, v1. X direction displacement at each node, y direction displacement at each node, and z direction. Similarly here, x direction displacement, y direction displacement, and z direction displacement. So 3 displacements. Okay. So this one is a truss element in 3D, but if we apply a load somewhere like this one, we also have to find rotation in x direction, rotation in y direction, rotation in z direction. Okay. Similarly, rotation in x direction, sorry. So ux1, let's say, and rotation in y direction and rotation in z direction. Similarly, we have to find here rotation in X direction at its second node, rotation in Y direction second node, and rotation Y direction, rotation Z direction, okay, at the second node. So at each node, we have to find 6 variables for general line element, okay. So this can be applied for any body, not only a body subjected to tension or compression, bending also, and also type of load can be axial load, or it can be like this one, irregular load, random load, okay. Not only acting perpendicularly, this is also subjected to tension and compression as well as bending. So then at each node we have to find 6 variables. So X direction displacement, Y direction displacement, W direction displacement, Z direction displacement, and X direction rotation, Y direction rotation, and Z direction rotation. So 6 degrees of freedom. So this one is called frame element, okay? Frame element. So frame, or generally beam element, okay? Beam. So beam. So just beam means in FEM textbook, they just specify pure bending problem, okay? Pure bending means perpendicular. Exactly, the load is perpendicular to the axis, okay? That is a pure bending problem. But not pure bending. Instead of bending, we also, in addition to bending, we also have axial loads like X and Y direction. So that is the line element. Okay, when we use line elements, when the cross-sectional dimensions are very, very small compared to the length of the body, the cross-sectional dimensions are very, very small, then we use a line element, okay? Line, just work in a line, like work with line body to save the time. So next type of element is two-dimensional bodies. So two-dimensional surface bodies. So two-dimensional surface bodies. When we use two-dimensional bodies, okay. So here, two-dimensional analysis, we can consider plane stress analysis, plane strain analysis, and axisymmetric analysis. So what is plane stress analysis? Suppose here, we apply load here, okay, and fix it. So we apply load here, and this thickness is very small. Thickness T is very, very small. Okay, we apply load like this one. So thickness of this plate is very, very small, and apply load exactly like this. Okay, in a plane, the force is in a plane. So only force direction is only in XY plane. Let's say XY plane. It can be like this one, or it can be like this one. Okay, FX and only FX and FY components are there. There is no FZ component. So then we can consider if the thickness is very small and the plate is free. Okay, the plate is free, fixed here. Okay, and force is only in two-dimensional plane. So then we can consider a plane stress. So we can convert three-dimensional body into just two-dimensional body like this one and apply mesh. So plane stress element. So there are two types of elements here: triangular element and quadrilateral element. Okay. So triangular element means just consists of 3 nodes. Okay. And quadrilateral element consists of 4 nodes. Okay. 4 nodes. So depending on the type of body, you can either use triangular or quadrilateral. Okay. So generally 6 node triangular element is in the middle. Also we just consider this one is non-linear triangular element. Okay. Non-linear in the middle also for more accurate solution. So similarly we can apply plane stress or plane strain. So when we apply plane strain condition, so if the body is very thick, okay, the body is very thick, and here this Z direction, okay, here this one is Z direction, fixed. Okay, I mean the length is fixed. So plane stress means sigma z is 0. Okay, sigma z is 0. Sigma only we have sigma x and sigma y. Stress in x direction and stress in y direction, and rotation tau xy. Okay, so plane strain, what is epsilon z is 0. Epsilon z is 0 means when the body is very thick body and it is fixed. Okay, fixed means the direction is not changing. Oh, sorry, the length in the z direction is not changing. That means strain, right? It is fixed means strain in this direction is 0, sigma z is 0. So then we can convert this body into this body. Just consider a middle plane or anywhere, here or here or here. So just apply a two-dimensional analysis. So this one comes under the plane strain analysis and axisymmetric analysis. So what is axisymmetric? So let's consider a cylindrical body, okay, like this one, cylindrical body. And so suppose rotating and the load is applied like this one. Okay, in what we say, so just load is applied in only plane, this plane. Okay, so like load is applied circumferentially like this one. So then instead of considering a three-dimensional body, just consider only strip of this one. So this one is axisymmetric. Okay, axisymmetric analysis. Okay, so just like this one. Oh, sorry, yeah, this is the body. We just model this body. Okay, only strip. So axisymmetric is when we apply this cylindrical type of bodies and spherical type of bodies, round bodies, spherical type of body. So we just consider a strip. Okay, so that is axisymmetric. Okay, so this is a two-dimensional surface body. What type of elements we use? Triangular and quadrilateral. And what we have to find here? So U1 V1 and U2 V2 and U3 V3. At each node, 2 degrees of freedom. Okay, so displacement in x direction, displacement in y direction. So we can consider a two-dimensional surface elements for plane stress analysis and plane strain analysis and axisymmetric analysis. So we have to assume based on either, yeah, you can consider a three-dimensional body. So for this case also, you can consider a three-dimensional body or just consider a line body. That's up to you. But to save time, we are using a line body, okay, instead of real 3D body. If the dimensions along the length direction is very, very large compared to the cross-sectional direction. Similarly here, to save this time, we just considering a two-dimensional planar body in these three cases, okay, plane stress and plane strain and axisymmetric. And that is two-dimensional surface body. And three-dimensional surface body is what? So there is a difference, right? Two-dimensional surface body means the body is like, okay, and forces are acting like this one, only in a particular plane. So like this one. Suppose here, let's consider this one is x and y. So only fx and fy components are there, and the body is very thin. Then we can consider two-dimensional surface. But we also have fz, okay, force fz. Try to bend this, okay. So try to bend like this one, okay. Try to bend like this one in this direction. So then we have to work with a shell type of element, okay. Shell type of element is nothing but, so plane stress analysis, but plane stress means only we work in a particular plane, okay. So shell element means we also have a bending moment, okay, bending moment. So like this one. So bending, okay. So there are two types of elements here, plate and shell element. So plate is nothing but if the body is flat type, like a flat tank, okay, flat tank. So water tank we consider, and if it is a flat tank, flat, then we consider just plate element. Okay, so instead of model using a three-dimensional, just this is a three-dimensional body, right? Three-dimensional body means there is a water inside. Okay, water inside. So we can consider a three-dimensional, complete three-dimensional body. Okay, also we can just consider a like this one, only this portion, just shell. Okay, only consider inside portion. Okay, so we use shell element if the body thickness is very small, and that is also subjected to bending. Okay, yeah, bending forces. So this is a plate element. Plate element means flat bodies, shell element means round bodies. Okay, so here also the element types are same, quadrilateral and triangular elements. So those are the different types of elements, 3D surface bodies. And so finally, final bodies, ultimate one is 3D body. Okay, so 3D solid body. In all cases, you can also consider 3D solid body. In this case, we can consider 3D solid body. In this case also, we can consider 3D solid body. And in this case also, you can consider 3D solid body. But our ultimate aim is to reduce the number of elements and the simulation time, reduce the simulation time. So that's why we are assuming something, and we are using a line element or plane stress or plane strain or axisymmetric analysis or shell type of analysis. The final one is three-dimensional body, so real body. So if you don't want to use any kind of those line elements or shell elements or the two-dimensional surface elements like triangular or quadrilateral elements, we just model a body using a 3D solid body. Just consider a 3D solid body and just model as it is. So you want to work in a real three-dimensional. Okay, so this will take time. Okay, compared to previous analysis. I mean, only particular cases we can assume this. So these things only applicable for particular cases, like very thin bodies. Okay, very thin bodies, and plane stress and plane strain also, like and this one very slender bodies we can apply line elements. Okay, very thin bodies we can apply shell elements, but we cannot apply for all type of bodies. We cannot apply shell elements or line elements. So yeah, we have to consider real model and model with 3D solid elements. So 3D solid elements, we have different elements: tetrahedron, hexahedron, and pentahedron. So this one is more suitable for curved shapes. Okay, curved shapes. Tetrahedron is more suitable for curved shapes, and hexahedron also suitable, sometimes suitable, and sometimes we use combination of this one and this one. Okay, if there is a complex shape here, okay, complex shape, so we combine this one with this one. Okay, combine this one means some elements we use here where the corner is very the radius of curvature is very small, very high, then we use tetrahedron, and we use hexahedron other places. Okay, combination also we can use. Okay, so tetrahedron, 4 nodes. Okay, at each node we have to find u1, p1, and w1, 3 displacements. Okay, so 4 node means 4 into 3, 12 degrees of freedom we have to for tetrahedron. Similarly, hexahedron has 8 nodes, 8 into 3, 24 degrees of freedom. So pentahedron, 6 nodes, 6 into 3, 18. Okay, and also these are linear nodes. Okay, I mean linear elements. Linear. So linear elements are not good for solving, because we have some stress discontinuity. Okay, when we use linear elements, But if you use a nonlinear element, I mean, if you consider another node in between two nodes, in the middle also, if we consider another node, it's a nonlinear element, okay? Nonlinear. So the nonlinear element is more suitable for curved bodies, and when there is a stress discontinuous, we can use nonlinear. So generally we use nonlinear. So generally FEM software, okay, ANSYS use nonlinear element, okay. Okay, this is the end of this hour, and the next hour I'm going to explain what kind of problems we solve during the remaining days, okay, problems to be solved, okay, and the next day, tomorrow, day after tomorrow, and the day, the fourth and final day. So what are the problems we are going to solve will be explained, okay, in the next hour. So I think this one is very lengthy lecture.